Hello everyone, welcome to a small presentation that I decided to do more or less spontaneously because I was missing a video for Sunday, so I decided to quickly put one together. I saw a video from Flatzoid recently where they talk about entropy, and it was so embarrassingly wrong that I thought I would give a desperately necessary explanation of entropy for flat earthers. Well, it's for flat. I wrote it down here for flatzoid, but I realized, well, it's basically for any other flat earther because none of them I have ever heard from them an accurate description of what entropy is, and their knowledge of gas physics fits on the back of an envelope. So But let's talk a bit about it. I'm of course Olaf from Olaf das Astro. Hello. I'm currently working on my master's thesis in astronomy, and I'm also in the master's course in physics. And I've done quite a few lectures regarding gases and aerosol physics and stuff like that. So I thought I could share my quote-unquote expertise with you all. I also did thermodynamics, which was where we talked about entropy. So let's actually talk about entropy. I have here 3 different definitions that I agree with. From Wikipedia, entropy is a scientific concept as well as a measurable physical property that is most commonly associated with a state of disorder, randomness, or uncertainty. That's from the English Wikipedia page of entropy. I have another one from a book from the Cambridge University Press. Entropy is a central concept for many reasons, but its chief function in thermodynamics is to quantify the irreversibility of a thermodynamic process. That's from a student's guide to entropy, a book that helped me understand entropy a bit better because I thought the explanation that we got at university was a bit superficial, at least in the beginning. We got a way better one a bit later in the course, but and I have here from the Oxford English Dictionary, when you look up entropy and you get to the definition that says in physics, a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work, often interpreted as a degree of disorder or randomness in a system, or in the system, Now all of these are statements that I agree with. However, when you look at flat earth videos, one of which will be linked in the description, you often hear things like the process of entropy, or like entropy happens and things like that. And I want to make one thing extremely clear. Entropy is not a process. It's a concept or a quantity, something that is in principle measurable, usually through other quantities such as temperature, internal heat, pressure, volume, things like that. But entropy is a quantity, not a process. Extremely important. So what is entropy really? Well, it's a sometimes conceptual quantity for disorder or randomness and things like that. The unit for thermodynamic entropy is joules per Kelvin, and I have listed the equation here, not that anyone will do anything with it, I just thought it is important. That's for irreversible closed systems, so that's a real case scenario. That's from the second kind of law of thermodynamics. I would like to add here, though, that usually idealized it's with an equal sign, not a greater, but in real life it's greater. So the higher the entropy, the less ordered a system is. So high entropy means low order. And in equilibrium, that's one of the takeaway messages from the second law of thermodynamics. In equilibrium, entropy reaches its maximum. So in the given system. So if in equilibrium is meant to be, imagine you have a cup of warm water and a cup of cold water. The entropy is very low in that case, and then you pour them together into one cup. And the one parameter that is kind of important here, the temperature, equalizes. So now the temperature is in equilibrium, and entropy will have reached its highest value, its maximum that is allowed within the system, of course. So the surrounding parameters of the system limit how high or low entropy can be. In case of our cup thought experiment, if the two cups, like the water in the 2 cups, is warmer to begin with, the entropy will not be the same as if the water in both cups is a bit colder. Okay, now with that, what's the law of entropy that Flatzoid refers to in his video, and that I've heard other flat earthers, like questionable education, refer to as? There is no law called the law of entropy. Sometimes the second law of thermodynamics is expressed as the law describing entropy. So I assume that that's what you mean. Could you confirm that for me, please, in the comment section, since I am actually aware that flatzoid watches some of my videos. So if it is, could you just say yes, and thank you for watching, of course. The second law of thermodynamics essentially just says that the simple version, the first version from Clausius, essentially says that heat always travels from hot to cold, which it does, you know, but in more general, with that's the broader definition, that's not just about heat. If two systems come in contact, the total entropy of the system will increase until its equilibrium is reached, or at least until a maximum is reached. The equilibrium that I have here is in an ideal unrestrained system. A more correct statement would be, in contact, the total entropy of a system will increase until it has reached its maximum that is allowed within the system. Now I have here something that I heard Flatzoid say that made me make this video in the first place. Gravity can't overcome entropy. That's what Flatzoid has said here, and it's a horrible, extremely malformed sentence within physics. First of all, here you have a force can't overcome is not a scientific term. What do you mean with overcome? And entropy is a quantity. This sentence is like saying magnetism can't lay off humidity. It makes absolutely zero sense whatsoever. This sentence is extremely malformed. I think what you mean with it is, if the second law of thermodynamics applies and gravity is real, why is there not an equilibrium in pressure between Earth and space? Because we say, like the globe size says, that we have both. We have both thermodynamics and gravity. So from thermodynamics, we should have an equilibrium, kind of, but with gravity, it says everything should attract to. Seemingly, these two contradict each other. They really don't, but that's as far as a flat earther gets. So, to conclusion, either thermodynamics is wrong or gravity is wrong, and since flat earthers only find evidence for thermodynamics, they reject gravity as thus being false. Now, there are so many problems with this argument. I will start with the macroscopic one. First of all, the maximum entropy of a system is not necessarily the equilibrium position, especially not on short time frames. Also, the change in entropy is not an instant process. Flatzoid imagines entropy to just rise instantly as soon as two come into contact. But it's not said that you know, it happens instantly. As long as it eventually reaches its maximum, the conditions are sufficiently fulfilled. So with you saying that, well, the gas should rush out and fill the vacuum, eventually it will, you know. that's like on extremely large time scales. We're talking about billions and billions and billions of years. Some destructive event will probably happen with the Earth, and our atmosphere will be washed away out into space. The condition is then satisfied. Entropy, fun thing for you to note here, Flatzoid, entropy can even decrease in some parts, as long as it doesn't decrease in the whole system. If you put coffee, you don't reheat coffee. Let's say you put a cup of milk in the microwave, right? And then when you take it out of the microwave, it's suddenly warmer than the surrounding air. Thus, the entropy just punctually of that small system, like the cup microwave system, has decreased even. Well, how does that work? Well, because you've invested energy from the microwave that's not thermal, that's in that case electromagnetic, to get it in there. But when you look at the whole system, you heating the cup of milk, including the electronic lines, like the source of the electricity and so on and so forth, entropy will have increased again. But locally it can decrease. That's fine. That's not a violation of thermodynamics. Also, entropy increases as we speak. We lose bits of atmosphere, of gas, each second. There are roughly 30 kilograms per second of hydrogen is what Earth loses to space, and a couple of grams of helium, which, curiously enough, is due to their lower mass. That's funny how that works, isn't it, Flatzoid? Almost as if there is some kind of force keeping the heavier gases at the Earth. Oh, that's bizarre, isn't it? There are also microscopic problems. Gases are molecules and they clearly have mass. I am pretty certain that you acknowledge this, flatzoid. Gravity acts on that mass. So clearly it is being pulled down, right? Many quantities actually rely on this. The fabled scale height that I talk about a lot because I really like the quantity. And the barometric pressure prediction, which works extremely well on the globe with just two assumptions, right? A whole bunch of meteorological laws that help us predict the weather. All of those rely on the fact that we know how gases act and that gravity interacts with the gases. That's nothing new. Like, not at all. We cover this in school, even in some places. So, there is also a problem with the good old container argument that flat earthers love so much. So gas pressure can only exist in a container and guff like that. First of all, no. There is an experiment where you put heavy gas in like a long pipe that's vertical, and at the bottom the pressure is higher than at the top, even though it's clearly not closed because it's open at the top, So that's not a closed container by any stretch of the imagination. Neither is Earth. So what happens at a container wall? Because I find it so fascinating, right? That because you stop thinking at the container wall. At the container wall, when a particle gets to the container wall, a force is exerted from the container wall on the particle. The momentum of the particle changes. So clearly you do not have a problem with forces changing the momentum. However, with gravity, which just doesn't act as quickly or as strongly as the electromagnetic force, somehow you have a problem. Why is electromagnetism okay with changing the momentum of a gas particle, and gravity isn't okay suddenly? Could you please explain it to me? There are more problems with that, not from a necessary physical standpoint, but like from a surrounding standpoint, which is do you really think that if it was that obvious, physicists didn't pick up on this yet? I can show you my course material from thermodynamics, and I would be extremely pleased if you could show where all of that is wrong, and I would also be extremely happy to ask you a few rudimentary questions from my entry to thermodynamics course, if you would feel like that, which you won't, obviously. Also, you do not have any mathematical formulation for what you think is wrong, so thus you don't even have a real prediction, which in itself is a problem. You can only cite small experiments with small-scale gas laws as evidence, which no one is denying. We aren't saying that gas doesn't behave like you show on small scales. We're just saying that on the small scales, gravity doesn't play a big role. And you are ignoring whole fields of physics, aerosol physics, meteorology, if you can count it towards physics. Some people count it towards earth sciences. I think they're more related, but that's not the part. You ignore whole fields of science and of physics, because the fact that gravity attracts stuff like gas and things is very well known and yields predictions that we use to calculate stuff. So in conclusion, your argument is rooted in a severe misunderstanding, and I believe in scientific, especially physical, like not non-physical in regards to your body, but in regards to physics, illiteracy. Your process of thought has to be something like, no scientists have picked up on it, but I am right, like without a shadow of a doubt, I know better than all of the scientists, which kind of sounds like a misled sense of grandeur to me. And why don't you calculate it or anything for us regarding the matter? Why don't you give us a prediction of what should happen according to you with quantifiable numbers? I've written my guess at why you don't do that right here, but that's just my guess. I'm happy to be proven otherwise. And with that, I believe we are at an end of this presentation. I thank you very much for watching. If you enjoyed this video, or you want to see more videos like this, please do consider leaving a like. And if you enjoyed it a whole bunch, maybe I can get you to consider subscribing. And with that, I will see you in the next video. Goodbye!